week was book heist. So I'd like to talk about that. And of course, any other questions that come up during the course of the session. So I just need a moment to just make sure I have the correct descriptions. Yeah, so Mr. Akshay, we can start the live stream on YouTube as well. It would be great if you could share the link of the YouTube live stream with me in the chat so that I can check if there are any questions on YouTube as well.
Started, ma'am.
Okay, we have started. All right.
Moment to.
Okay, I think I did not realize that we're already live on YouTube. So a very warm welcome to everybody who is watching on YouTube. What we are going to do today, I think, unfortunately, it keeps saying that my screen share is paused. So let me just trying to figure out a way where I can see both YouTube and keep my screen share alive. So just give me a moment. So I figure that out. Okay, so I think my screen share is back and I can see YouTube on the other screen. Yeah, hi, Biswajit, good evening. Thank you for joining. So I will see if I can just open up the week 3 programming assignments to begin with, and believe we have 2 of them. Week 3 was when we were discussing greedy techniques. So let me put that out. So I think we've also had the week 4 programming assignment deadline has also passed. So we'll see if we have a chance, if we have enough time, we might discuss that as well. So, okay, the first one was, I believe, fixing gadgets. So let me just recall what the problem was. So, okay, maybe I'll just start this off here. So what was the problem? We have a gadget service center. There are K counters numbered 1 to K. The staff addresses complaints of the customers. They tried creating a token system so that the customers could wait for their turn, but they discovered that all of their customers were impatient and superstitious. So each customer that visits the service center has a strongly preferred counter P. Okay, so customers. Customers have preferred counters P based on whatever number they consider lucky. And because they're impatient, if they find that their counter is already occupied, then they just go away, right? Now, the owner wants to maximize the number of customers that they can actually serve. So you want to maximize the total number of customers that get their gadgets fixed. You want to, okay, so I think the optimal word is misspelled in the problem statement, but you want to help the owner with coming up with a problem, with an optimal strategy. So you have to, of course, reject some customers. You can't help everybody. So you're given a list of N customers with their arrival time, departure time, and their preferred counter. And you need to calculate the maximum number of customers that can be accommodated by the service center. You can assume that all the customers bring in equal profit. So it's not that one customer would be like, so there there are no weights on the customers. All customers are equal in terms of how much they bring to the table. So here's what we have. So n customers. And you have their arrival and departure times as input. And there are some edge cases here. The ith customer wants to occupy their favorite counter from the time that they arrive to the time that they finish, where PI is inclusive. So let's say, sorry, SI. So let's say this is SI and FI. So this is start and finish, if you like. So the ith customer occupies PI during SI, FI, which is to say SI is inclusive and FI is exclusive. So at the time instant FI, somebody else can take over. Okay. So I'm not sure if I'd like to go over the test cases or the examples. We could do that. Let me just check if there are any questions here about the. Oh, okay. So there's a question in the. All right. Good evening, everybody. On YouTube, how can you join the Zoom? I think the Zoom link was shared over email and also in the Discord group. So if you have access to either of those, which you should, if you have registered for the course, then you can join us on Zoom. Let me just quickly check if there are any questions on Zoom. Can you give me a +1 if the problem statement is clear, or if you have any questions about the problem statement itself? Okay, all right, thanks, Vijay. So good. So yeah, let's maybe quickly walk through one of the examples. There were like a couple of sample tests, I think, that were given. Okay, I think again my screen share is paused because I lost focus on the window, so it should be back now. Okay, right. So the first sample examples here. So let me just go over the notation ones. N and K are the first. So N is the number of customers and K is the number of counters. So the first thing you have is N and K. So 3 customers, 3 counters in the first example. And I think the next N lines have SI, FI, and PI. So arrival time, departure time, and what the customer occupies, what's their favorite counter. So in the first test case, you can see that the preferred counter, so you have some arrival time, departure time. I'm not even going to bother writing it down because the preferred counters are 1, 2, and 3. So it doesn't really matter when the customers come and go because they all like 3 different counters. There are 3 customers and 3 counters. So nobody's stepping on anybody's toes. Everything is fine. So you can serve all the customers here without any problem. In the second test, N is 4, K is 2. So you have 4 customers. The first one comes at the 10th time step, leaves at the 100th time step. And their favorite counter is 1. And this is the only person who likes counter 1. So intuitively, there's no problem in accommodating them. For the others, everybody else likes counter 2. The first one comes at 100, leaves at 200. The second one comes at 150, leaves at 500. And the third person comes at 200 and leaves at 300. So among these 3, clearly we cannot serve everybody because if you think about drawing it on some sort of a number line, so from 100 to 200 might look like that. And then the second person wants to occupy the second counter from 150 to 500, and the third person from 200 to 300. So hopefully it's visually clear that you can't accommodate everybody, but what is the maximum number that you can accommodate? So let's give these customers names, the first customer, the second customer, and the third customer. So how many customers do you think you can accommodate, given that this is when they come and go and they all want the second counter? Two, 1, and 3. Yes. Okay. I first thought you were saying you can do all 3 of them, but no, you're right. The maximum number of customers you can accommodate is 2. And that would be the first one and the third one. Notice here that at time step 200, the first customer leaves and the third customer comes in. It's not a good idea to try and accommodate the second customer, because the second customer ends up blocking the other 2. And if you were to try and accommodate the second customer, you would have to give up on the other 2, right? Okay, so now in general, we want to come up with, so I think we agreed earlier that the problem statement is clear. You can also think of this in terms of, like we just drew these intervals, I think is a helpful visualization. So let me just draw a line here for you and just say that these are your timestamps. And let me just draw out an abstract example here. You may be, I mean, seeing these intervals may remind you of Islands War, which is a problem that we had discussed, I think, in one of the videos. And I think there's some similarity between this problem and that one, but anyway. So you can think of these intervals as representing when customers come and go, right? And what are you looking for? What does the answer represent in terms of the number of intervals? You're looking for a maximum collection of what? What kinds of intervals are you looking for? Notice that if you pick this, sorry. So if you pick this, you automatically cannot pick any interval that overlaps it. So yeah, exactly. So I think Vijay's answer here is what I was looking for. You're looking for a collection of intervals that are mutually non-overlapping, that are mutually independent. So you can think of, so that's essentially what this problem boils down to. And I suppose you could think of a number of different natural greedy strategies for picking up. So you want a largest, so let me just write down the goal again. So the goal is to find the largest collection of mutually non-overlapping intervals. Yeah. And let's just try maybe a few natural greedy strategies. So greedy strategy 1 would be to pick maybe the shortest interval first. Because your intuition may be that a short interval doesn't overlap with any other intervals. So what do you think? Would this work? Give me a +1 in the chat if you think it would work. This goes to people watching on YouTube as well. Feel free to interact. While I'm waiting for a response, so hopefully, yeah, okay, -1. No, it wouldn't work. So does somebody have a counter example for why it wouldn't work? Kushagra is saying it might not. Yeah, that's, yeah, it turns out that it actually wouldn't work. So let's maybe draw a quick example to see that it wouldn't work. So you can have a really tiny interval like this one. Or maybe let me just, not so tiny, something like this. So if you picked the shortest interval first, you would pick the orange one, and that would block out both of the blue intervals, right? So that's, I mean, that's not the optimal answer. You would want to pick both of the blue intervals, even though they are longer. Does that make sense? Give me a +1 if it makes sense. So Code Desire is asking if competitive programming is necessary for job perspective. So we have addressed this in like some of the early videos, Code Desire. I think it's not necessary and not sufficient. That's what I say typically. It helps, but there are other ways also to prepare for jobs. And maybe you want to look at some of the earlier videos to see a more detailed discussion about this issue. Okay, great. So the shortest interval first approach doesn't work, even though it is sort of tempting. What else? What would, how about the interval that has the smallest number of overlaps with other intervals? Yeah. So this also feels very natural because for every interval, I can count how many other intervals are you blocking. And, people who are not blocking too many other intervals, it seems like we should prioritize them because they probably give you, they give you the maximum breathing space to pick other intervals. They create the fewest conflicts. Yeah. So what do you think? Do you think this would work? Okay. So Dhanshu is saying no. And Rahul is saying yes. I'm not sure if it was answering my question because there's always a lag in YouTube. So I don't know if you were answering the previous question. Kushagra, you're saying that this might work. So Sudhanshu, do you have a counter example? I had a counter example. Yeah, I do have a counter example, but I'll have to, okay. So Sudhanshu, if you want, you can describe your counter example and I will draw mine. So we have already started saying counter example. So you may have guessed that, it's not going to work. So let me see if I can draw this out. So just give me a minute because it has a few different intervals. So and Sudhanshu, please feel free to share yours in terms of numbers. I'll be happy to draw it, try to recreate it. But hopefully this is visible, and maybe I'll just give these intervals some names. So Okay, so now that these intervals have names, which interval has the fewest conflicts? So this was, let me just recap that this was the greedy strategy that we are proposing. M, exactly. So M has the fewest conflicts with other intervals. So we will try to pick M first. And once we have chosen M, notice that we have blocked, what have we blocked? Well, we have blocked X and Y. And after this, notice that we can only pick two more intervals, right? So one is from this group. The other is from this group. I mean, using this greedy strategy or using any other strategy. In fact, let's just follow this greedy strategy. What it's saying is pick the intervals with a fewest number of conflicts. But right now, every interval has the same number of conflicts. So it doesn't matter what you pick. So you'll be able to pick one interval from group one and one more from group two. Nothing more than that really. Okay. So basically, how many are you able to pick if you follow this greedy strategy? If you follow the greedy strategy, you can pick 3. But on the other hand, what is the optimal answer? The optimal answer is 4. Yeah, thanks, Vijay Kushagra. It's kind of visible, right? Optimal is 4 because you can pick W, X, Y, Z. So even though this greedy strategy looks very tempting, it actually is not, it doesn't always work, right? Okay, so, and I'm sorry to have to drag you through all these greedy strategies that don't work, but I'm doing this because, it may have occurred to some of you. These are very common strategies that sort of come up when you start thinking about this problem, right? So Kushagra, that's exactly what, okay, so you're saying, you're saying you can remove those having most number of overlaps. That even in this example would be a bit dangerous to do, right? Because if you notice, the intervals that participate in the final optimal solution actually also have the maximum number of overlaps, right? For example, if I were to write down in the original example how many overlaps these people have, so W is overlapping with 3 other intervals. P is overlapping. Okay, so I think, okay, so sure. Actually, although in this example, it might actually work, I'm not sure. So M is overlapping with 2. X is overlapping. Yeah, okay. So X is overlapping with actually quite a few, I think. Oh, yeah, again, 4. It's not overlapping with W. This is 4, right? P is overlapping with Q, R, W, and X. Z is overlapping with ABC. So I've just written down the number of overlaps here. So if we follow the opposite greedy strategy where we say, let us eliminate those which have the maximum number of overlaps. If you're lucky, you will eliminate PQR or ABC, but if you're unlucky, you will eliminate X and Y. And also another question is, where do you stop, right? So you've eliminated, you keep eliminating maybe until there are no overlaps left. If you do that, then in the worst case, because your greedy algorithm will probably break ties arbitrarily because it doesn't have really a reason to favor anything over anything, unless you bring in some tie-breaking rules, but we don't have any tie-breaking rules yet. So right now the greedy algorithm will see that there are these 8 intervals which have the maximum number of overlaps, which is 4. So it may choose to knock out, say, X. Y will still have 4 overlaps. In fact, PQR ka number of overlaps will reduce to 3, I think. Y still has 4 overlaps, so Y may get knocked out next. So you're left with M now has 0 overlaps. And then again, it doesn't matter what you delete, but you might delete PQR and ABC and you'll be left only with W and Z. So in fact, that's a nice one that I never really brought up before. So I'll add this to my collection of greedy strategies that may not work. So greedy 3 would be, this feels like somehow the opposite of greedy 2, but it seems to lead to different solutions. So I'll put it as a separate strategy. So eliminate intervals with max overlaps till no overlaps left. And this is the same counter example as before, so this also does not work. Okay. Let me propose another fun one, and the reason this is a fun one is because the correct answer is very close to this. So it's a spoiler alert. You may have guessed that this will again not work, but let's see. Pick intervals that start first. Okay, so the interval that starts the earliest, right? I will pick that interval first, eliminate everything that overlaps with it. Then again, I will pick the interval that starts. So the first customer to come gets priority, right? Like the first assignment you got gets a priority. The next, then you finish that. And then you may have had to sacrifice all other assignments that you couldn't multitask on. And then you look at and you repeat. That's probably not the best analogy, but anyway, it's at least funny a little bit. Yeah. Okay, so right. So what about greedy 4? Does it work? Yeah, right. Vijay is saying, yeah, you can take like the first customer to start, maybe somebody who is just like really keen staying on forever. So this will be a problem. And then, you know, you may have all of these smaller intervals. So you may miss the optimal by a big number. Yeah, I mean, you know, you can make this look really bad compared to the correct answer. So the interval that starts first is this one, and it blocks everything else. And yeah, so this is definitely not a good idea. But the reason I said this is close to what works. So does anybody have a suggestion for what works? Because some of you may have resolved this problem during when you were solving week 3. So what worked for you? What was the greedy strategy that worked for you? Pick intervals by shortest end time. So in some sense, pick intervals that finish first is actually what works. Right. So you look at the interval. Look at the interval with the earliest finish time, pick intervals that end first, exactly. And, you know, then you can kind of get rid of everything that overlapped with it. It turns out that this strategy is actually the best possible. Now, before talking about why does this work, because we looked at a lot of convincing sounding greedy things and they didn't work. And now I can ask you, give me a counter example, and maybe all of you will struggle to find a counter example, but that is not a good enough reason to say that that's why this algorithm is correct. Ki none of us could find a counter example. You have to have a proper argument for why it works to convince yourself. Of course, if you're doing this in the middle of a contest, then there are two kinds of things. Either you have seen the argument before, so you kind of know that this is the correct thing to do, so you confidently go ahead. If it's a similar, like maybe it's a different story, but it's essentially the same problem, then hopefully, what you have seen before will help you. Or sometimes you just go with a gut feeling where, you try to find some counter examples, you can't, and then, you kind of hope that you have stumbled on the correct strategy. And I think that's often like 50-50. I think with experience, you can improve the probability of getting lucky. But I would say if your greedy algorithm turned out to be right and you don't know why, during the contest, I would definitely encourage you to sit down and, during up solving, try and convince yourself as to why it works. But before that, let me just step back a bit and make a note about the implementation. So remember, we said that there were K counters, and here I kind of got fixated on this example where all these customers were coming to the second counter, and then I said, well, among these you have to pick like the largest number of non-overlapping intervals. Right, so I see that Kushagra has a question. I will just, I think I will just try and get back to that in a bit, Kushagra, thanks. So I think what I was saying here is that we kind of ended up implicitly focusing on all the customers who are coming to counter 2, and we are asking, okay, what is the maximum number of customers that counter 2 can serve? But notice that what is going on the K service counter is completely independent, right? So every service counter says, okay, who are my customers? Who are the people who want to come to the IIT service counter, right? And the person who is at the IIT service counter only has to worry about maximizing the number of people who can be served at the IIT service counter. So whatever we are discussing here can just be, so in your implementation, you just have to remember to segregate the customers according to the counters that they are visiting. And then for each counter, you separately apply this greedy strategy. Okay. So at least in terms of what the algorithm is, ignoring why it works for now, but in terms of what we have to do, is that kind of clear? Give me a +1 if that's okay. Yeah, awesome. Okay, so now so the only thing that's left to figure out is, why does this actually work? Okay, great. So you can actually, you can actually formally prove the correctness of this algorithm, and it's actually not in spirit. It's very similar to the kind of discussions that we have had for Islands War. But intuitively, the idea is that, okay, so you're trying to find a maximum collection of overlapping intervals. And what I can do is, let's say that, we look at all the finish times where you picked an interval. So let's say this was, maybe the first interval that finished was F7. And the next one was, let's say, F3. And the next one was F9 or something like that. So here is at least one way of building some, I think, intuition for why this works. So let's just imagine dropping vertical lines at all the places where you picked, your solution. So your solution was maybe something like this. So my claim is that these three vertical lines actually end up intercepting, or they end up, they end up intersecting every single interval. Can you draw an interval which is not intersected by any of these vertical lines, right? Where would such an interval, so let's say, I don't want to cross any of these dotted lines, right? I want to draw a horizontal line that is not crossed by, and like it doesn't overlap with any of these vertical lines. So then that means, it has to start somewhere. Let's say it starts here, and then it has to finish before I reach this vertical line, right? It has to finish before I reach the next dotted line. So from wherever it starts, there is a dotted line that is next to it. So to avoid intersecting with that dotted line, I have to stop before it, correct? But if I end up stopping before it, then what is the contradiction? What is like, why can this not happen? Because remember how I drew the dotted lines, it was based on the choices made by your algorithm. So the algorithm said F7 was the interval that finished first. Then I erased everything that intersected with F7. Then the next interval to finish earliest was F3. I picked F3 and I erased everything that overlapped with F3. And then the next interval to finish fastest was F9. So I picked F9 and I deleted everything that intersected with F9. And at this point, all intervals are gone and my algorithm stopped in this example. So why can this pink interval, why can it not exist? Can anybody explain that?
Because it is stopping before F9.
Like, how does it contradict the behavior of your algorithm? And one hint is you want to think about how did the algorithm choose F9? Yeah, exactly. It stops before F9, as Kushagra has pointed out. The pink interval stops before F9. So if there was such an interval, then the algorithm would have picked that one. It wouldn't have picked F9. Yeah. Does that make sense, everyone? Because this is like kind of crucial to the intuition for why it works, right? So now, so based on your solution, so if you have picked k intervals, then based on these k intervals, you can draw these k vertical lines, which have the property that every interval is being like, you can partition, more or less, you can partition your set of intervals into these k groups with the property ki har group mein se you can pick only one interval, because all the intervals that are being intercepted by this vertical line, it means they're mutually overlapping, right? So you can pick only one from this. Similarly, all the intervals that are intercepted by the second vertical line, they're all mutually overlapping because they have that vertical line in common, right? So from that group also you can pick one. So essentially your k intervals have actually partitioned the entire set of intervals into k groups, with the property that from each group you can only pick one. So you couldn't have picked more than k. So any optimal solution, there may be a different optimal solution. I'm not saying this is the only one, but any solution couldn't have picked more than k because they're constrained to pick only one from each group. And how did these groups come about? Your algorithm has actually sort of created these groups for you, or you can create these groups based on the algorithm. So the groups are all the intervals that overlap with, that pass through where F7 ended, all the intervals that pass through where F3 has ended, and so on. And you know that you cannot have any interval that is not intersected by one of these lines. So does that make sense? Does that explain the correctness of the algorithm? Yeah, so Shishir Pandey in the YouTube chat, sorry, I saw your message just now. Yeah, indeed, the pink interval ends before F9, and that's the main intuition. So there are other ways of proving this as well. There's something called greedy stays ahead, and you can try to compare your solution with a greedy one, and you can do some exchange arguments and so on. And that's usually the standard textbook argument that you can find anywhere. This is usually a slightly less common way of saying it, although it's, I guess, yeah, depending on what you're looking at, I'm sure you can find this argument as well. I just find this more intuitive because it gives you a structural reason for why you have really, you have found an optimal solution. Okay, so if that makes sense, we are done with correctness. In terms of analysis, I think you have to do some sorting by endpoints and you have to clean things up a little bit. And you have to do it, I think, for every group. So I guess, so the running time, I guess, would be, well, the time it takes to sort, and after that should be more or less one pass, I guess. So yeah, I think something like n log n should cover the running time here, I believe. I think you may have to, the reason I'm thinking is because you may have to store things a bit carefully to make sure that, you know when to, like, what are the intervals you need to delete. Yeah. But I think this should be okay. Yeah. So the dominant part of the running time is in sorting the intervals by their end times, but this should be okay. All right. So that's fixing gadgets. Now let's talk about the next problem, which is book heist, which I think between these two problems is probably the one that requires a little more thought. So here I'll try to save you some time by not taking you through these sort of false positives, things that don't work. Let's just at least try and get the main intuition for a solution. And, if we can do a formal proof, I think I can just share that with you separately, but let's at least get to the point where we understand the problem and come up with a believable sort of a greedy strategy. Okay, so there's a book reading scheduled at a popular bookstore, and book lovers are expected to show up. So again, there are N customers once again. So each of them, try to write it properly. So this is arrival and departure time. Okay, maybe this was EI, not FI. At any point of time, the set of people who are present in the bookstore bond over books, coffee, and conversation and become friends. So at any point of time, everybody who is there, you can think of them as being friends. After the event is done, it turns out that some books were lost or stolen. So the police want to interrogate everyone who came, but they cannot speak to everybody. So N is large. So they are suspecting that there are X people involved in the theft. Yeah. And it's natural that these X people would be friends with each other. Okay. So now, again, this is the crucial part of the problem. They want to say is that they will schedule their interrogations so that for each collection of X friends, there will be at least one person who is interrogated from that subset. So they want to, okay, so you want to select the smallest number of people so that you have this property, okay? So, so you have all the information. You want to pick K people to be, I hope I'm spelling interrogated right, such that for any subset of X people, so I would normally ask you if you followed the problem description, but maybe let's do one example so that it's kind of a bit easier to understand. So right, so let's just do one of the sample tests, I guess. So there's N and X. So in the first sample, N is 3 and X is 2. So the first person comes in at time step 1 and leaves at time step 3. I hope this is enough. Okay, so the first person comes in at 1 and leaves at 3. The second person comes in at 3 and leaves at 5. And the third person comes in at 4 and leaves at 6. Okay. So now you want to make sure that, so if I look at these people though, yeah, what does it look like? So there's person 1, 2, and 3. So there is one point of time. So when are people friends with each other? I did not write it down, but at any point of time, the set of people who are present together. So I guess you would say that at time 3, 1 and 2 were present together. Yeah, this is like a bit of a corner case, but let's say that here I think it's SI and EI inclusive, unlike the other problem. Yeah, so I think we'll say that, 1 and 2 are friends with each other. Are 1 and 3 friends with each other? Clearly not, because 1 leaves at 3 and 3 comes in at 4. So they are distinct, so they have no overlap. They don't even meet at the endpoints. But 2 and 3 have a clear overlap. In fact, they're there for 2 time steps together. So 2 and 3 are friends with each other. So what did you want? You wanted that for any subset of 2 people, at least one person is interrogated. So what would be the optimal strategy here? Okay, anybody? Yeah, pick 2, right? Because if we picked 1, then between 2 and 3, we would still have to interview somebody else. And if we picked 3 again, between 1 and 2, we would have to interview somebody else. So it's better to pick 2 so that we only have to interview one person. So thanks, Debashish, that's correct. We only have to pick 2 to make this work. Okay, great. In the next example, I'll not draw the intervals, but I'll tell you what the friendship structure is. So you have 1, 2, 3, and 4. And it turns out that, this just everybody is friends with everyone. So everyone is friends with everyone, and X is 3. Okay. So, so what is the answer in this case? Can the answer be 1? Like, is it enough to interview one person? This is symmetric, so it doesn't matter whom we interview. But yeah, so it's not enough to interview one person, because if you just interview one person, then you will have like this group of 3 people who will be left out. So you need to interview at least 2 people. And it turns out that because everyone is friends with everyone, you can interview any 2 people and that will be enough. So so if you interviewed 3 and 4, then like every group of 3 people would involve either 3 or 4, right? So it should be okay. All right. So does the problem statement and the examples that we have discussed so far make sense? Just give me a quick +1 in the chat if it's okay. Let me know if you have any questions. Okay, awesome. Cool. So now let's think about what would be a natural greedy strategy here. And for this problem, unlike the previous one, I think the natural sort of greedy strategy is in fact fine. So let's just imagine that you are witnessing, so you are a fly on the wall and you're watching people come and go into this bookstore or wherever this party is happening, and let's just wait till, so people are coming and going, coming and going. The interesting thing is, let me say the first milestone is when X people in the room for the first time. Okay, so like previously, if so this is sort of an abstract example, but let me try and explain it. So let's say this is time t equals 1, t equals 2. What I'm trying to keep track of is how many people have come and gone. So let's say x equals 3. Okay. So let's say here the number of people in the room is 1. Now let's say one more person joined, then one person left, then one more person joined, one more person joined, one person joined, and then another person left maybe. So you can see number of people is changing, right? So this is okay. So as long as there are, okay, sorry. Hopefully this is still visible. As long as there's only one person, two people, one person, two people, I don't really care because I've not seen like a big enough gang. So I don't need to worry about this. But the moment I see three people together, then I get some anxiety, right? Why is this? Because now I know that at least one of these people I should flag, right? So I want to make sure that I interview at least one of these people. Among the three people in this room, if I had to pick one, intuitively, whom would you pick to interview? Like, I know that if I did not interview any of these people, then I'm in trouble because then I have dropped the ball. I have missed out on one collection of X people completely. So I know one of them I have to pick. Whom does it make sense to pick the most? Exactly. So I think Debashish is suggesting that the one who leaves last should be interrogated. So you look at these three people who are currently in the room, and then you see which one of them is going to leave the latest. Intuitively, this person you should grab because this person will account for the maximum number of three-sized subgroups. So Kushagra is saying the person who left at t equals 7, right? I should have maybe drawn a few more timestamps. So yeah, if I've not told you who is leaving when, but yeah, somebody joined, somebody left, and maybe more people joined, and somebody here was there till the very end. You would pick that person, as in this example. So yeah, it should have probably been a slightly longer example to illustrate it better, but hopefully you get the idea that among these three people, you ask everywhere, somebody says I'm leaving at 7 p.m., somebody says I'm leaving at 9, somebody says I'll stay till midnight. Then the person who stays till midnight is going to account for the most number of three-size subgroups. So it's good to tag that person. So imagine now that we tag this person. Just in principle, so when you're coding, you can build a set of marked people. Okay, so you mark the person who is supposed to leave the latest. Okay, and now in any future timestamp, what do you have to watch out for? You have to watch out for when the set of unmarked people exceeds X. So suppose here you had some three people, let's say A, B, C, and let's say A was the person who was leaving the last, and so you have tagged him, said that okay, you are going to be interviewed at the end. And now, as we said, somebody has joined. So A will anyway be interviewed, but now is it enough? So at the fourth time step, can we just let it go or should we take some action? So at the fourth time step, the situation is just like what we discussed here, right? If we don't mark anybody else, then from the group B, C, D, we may be in trouble, right? So in the fourth time step, so we need someone else. So in the fourth time step also, we are in a situation where there are at least X unmarked people, right? So we need to build our set of unmarked people. So again, among B, C, and D, we will ask, who among you will be here, till the after party? Who among you is staying till, for as long as possible? And hopefully they don't know why we are asking them this. So whoever replies, let's say, the person who came in next is going to be there even after B and C have left. So then we will mark them for being interviewed. Okay. At this point, actually, let me change this example a bit and say that, or maybe this is fine. So let's say it's 3 and let's say B has left. So we have A, C, and D. And let's say somebody else joins in the next time step. Sorry about that. So in the next time step, let's say you have A, C, D, and E. But remember, A and D have both been slotted up. So at time step T equals 8, do you have to do anything? Do you have any anxiety? At time step T equals 8, do you need to do anything? No, thanks, Kalpesh. No, you don't have to do anything because although there are 4 people, 2 of them have already been tagged from your previous work. You know that they are kind of witnessing. So ACD, CDE, ADE, etc. So there are these 6 groups of 3 friends each, but A and D are both accounting for all of them. So even though a new person has joined, you don't need to do anything. At some point, A and D will leave, new groups will be formed and so on. So you'll have to start taking care of things as and when they happen. But here's the idea of the algorithm, right? So initialize marked to, an empty set. And what you want to do is at each time step, if the number of unmarked people is strictly more than X, let's say the number of unmarked people is K, then mark. So I don't remember if you have one person coming in at a time or, at one point of time, you could have many people come in. Yeah, it could be a big influx of people. So you'll have to account for that. So the number of unmarked people, so if you have K unmarked people, and that's more than X, right? So then how many of these people do you need to mark? Well, so for instance, let's just do this with numbers. So let's say that you have 10 unmarked people, for instance. And let's say X was 7, okay? Then if you mark only 3 people, then you will be left with a group of 7 people that you haven't, interviewed anybody from. So you have to mark at least how many people? Number of unmarked people minus X plus 1, exactly. So it's going to be, I would say, K minus X is not enough. You need to mark K minus X plus 1 many people. This plus 1 is to just account for the fact that you shouldn't have a group of X people who are not interviewed. So that's why if you make sure that you mark K minus X plus 1, the number of non-interviewed people will drop to X minus 1, and that is safe. So mark K minus X people who have the what is the blank here? Who have the largest, smallest. EIs are the end times. That's the time when people leave. So what should I put in the blank? Largest, exactly. So you want people who leave the latest to give you maximum mileage in terms of, how much staying power they have. So this will have to be largest. That's intuitively the right thing to do. You want to mark these people, they will help you for the longest. So the next timestamp, you'll have some people come in, some people leave. And of course, some marked people may leave. So depending on how the situation evolves, at the next timestamp, you have to again check if, so you'll have to see if a few people come in, the people who come in are unmarked by default. And and then possibly some people leave. So if some people leave so let's say from the current situation, 5 people come in and 5 unmarked people leave, then you don't have to do anything. But if 5 people come in and 5 people leave, of whom 4 are unmarked and 1 was marked, then you have to mark somebody new. So you'll have to just keep doing this calculation again and again. But that's fine. So just loop over all the time steps, right? And at each time step, just check if the number of unmarked people exceeds X, then, mark K minus X plus 1 people, where K is the number of unmarked people. And so you want to make sure that you have a sense of who are the people who are leaving the latest and just mark those. And once you have reached the end, the size of the set of marked people, that is going to be your answer. So that's the correct greedy approach. It turns out that this approach actually works. And I would say it's reasonably intuitive, although I think it's not uncommon because this problem statement's a bit confusing. It's saying that for every subset of X people who are friends, you want to make sure that at least one person is interviewed. So it's possible to probably misread that statement, and then you might end up with slightly different approaches that will end up not passing the tests because the tests are designed for this version of the question. So at least at an intuitive level, please let me know if this algorithm or this idea makes sense. I think Kushagra already had the right intuition. Maybe some of the others who are here have already solved it as well. Let me know if this tallies with what you were thinking, and if the algorithm is okay, if it makes sense. Give me a +1 if that's fine, or if you have a question or a clarification, then please post that as well. So. All right, thank you, Vijay and Kushagra. So seems like maybe the algorithm is fine. One thing that I have not gone over is like a formal argument for why this is correct. Okay, I'm just looking at the chat. I think Shishir has also addressed the question correctly, the largest n times. And you're asking, isn't it similar to spanning tree sort of thing? I'm not sure how it relates to spanning trees, although maybe there is a way in which it does. Like the spanning tree algorithms are also inherently greedy in the sense that they expand you expand the reach of a spanning tree in a certain way, but I'm not sure how to immediately connect this to spanning trees. Devashish, that's exactly the intuition. Largest time because the person can meet more future people and minimize the interrogation count. Exactly. So the longer the marked people are people who stay back for the longest. So as you go along, more and more subsets of size K keep getting taken care of because they're just there to witness those subsets. If, for example, on the other hand, you mark the people who are going to leave the earliest, then you will end up, you'll end up marking a lot of people and you'll end up interviewing a lot of people. So one extreme example is, let's say you want to hit all subsets of size 2, or you want to interrogate all friends of size 2. And let's say you have like this one person, who came at 7 p.m. and stayed all the way up to 11 p.m. And there were these people who came and went, came and went, came and went, came and went. So, so the first time that we saw that there were 2 people, if we mark this person for interrogation, we'll never have to mark anyone else because all subsets of size 2 are taken care of. But if we did not mark this person and mark the person whose end time was the smallest, then we'll end up marking all these people, which is definitely not optimal. So that's, of course, just an example, an extreme toy example to make a point, or at least give some intuition for why you want people who stay back the longest to be marked. It's exactly what you said. They will meet more and more people, they will have more friends, and that's why they will account for more and more subsets of size X. And what you can argue for the correctness of greedy, the intuition is this, like at any point of time, you have to pick up k minus x plus 1 people anyway. Any solution will have to choose so many people for interrogation, because if they didn't, then the solution would not be correct. There would be a subset of people who were left out. So any solution will have to invest in interrogating so many people anyways. And the only problem is, could there be a solution that chose a different set of people? And therefore, in the future, maybe in the future, their requirement was less because they marked people in a more clever way. But you can show that because you have chosen the people that stay back the longest, nobody can really do better than what you have done here, except for, if you broke ties differently, but the situation will be exactly the same. So here you can do a more traditional sort of a greedy stays ahead kind of an argument, saying that what you have done here is actually future proof. It gives you the best numbers in the future. You never have to do more than what is required. So I am definitely skipping like a formal argument. You have to probably throw a bunch of notation at this and say it more properly. But at least the intuition for what the greedy strategy should be happens to be the right one here. But as we have seen in the previous examples, a lot of intuitively appealing greedy strategies are not right. So I'm being a little bit hypocritical in saying ki intuitively sahi lag raha hai to sahi hoga. We should not stop there. Ideally, you want to properly argue this. But we are kind of almost going to be 15 minutes over time. So I will not bore you with the formal proof here, but I'll see if I can do a bit of a write-up for you and share that in due course. But hopefully you're convinced about the approach at the level of a gut feeling. And implementing this is it's not very hard, but I would say it's also maybe not completely trivial. It's not like just one for loop or ho gaya. Matlab, you have to do a little bit of work in terms of, keeping track of things. So sorry if it was a slightly annoying implementation. I think I have a version of it that's kind of commented up a little bit in either Python or C++. I forget. I'll share a version of that. I think somebody on YouTube was also asking for programming solutions. Yeah. And okay, so yeah, I think that is something that we'll start putting out soon. Gaurish, the Discord link, unfortunately, if I post a link in this YouTube chat, it will not show up for you. You can find the Discord link on the course website, as well as if you've been getting the announcement emails from NPTEL, look for an email which says welcome to the course. And the very first one is a very long email with a lot of links. And the Discord link should be a part of that email. So I hope you can find it. And Mahesh, unmarked is always greater than X. Actually, not necessarily. For instance, if X is 5 and in the first 3 or 4 time steps, you only have one person coming in, the number of unmarked people is going to be less than X. So we're just saying, this is just notation. We're saying, let us use K to denote the number of unmarked people, how many ever are there. Whenever it exceeds K, you have to make sure that you add so many people into your marked set to maintain the invariant that the number of unmarked people is always, in fact, strictly less than X. You want to make sure that it's always less than X. So I hope that that made sense. All right, everyone. So yeah, I think with that, we sort of come to an end of the description of the algorithm. So, and as I said, modulo a formal sort of an argument for correctness. Hopefully, at least we walk away with an understanding of what needs to be done. So in case you're in a situation where you didn't have a complete solution to this problem that passed all the tests, then I'd like to encourage you to try and implement this. We don't have any spoilers yet. I don't think we have released code for this. So, you know, whenever you have a chance, just try it out. I think we should be able to release solutions to most of the programming assignments pretty soon. And also because of some logistic hurdles, we will be doing a combined release for the programming assignments for week 5 and 6, and there'll be only one assignment each because of the fact that it was released late, but there will be enough practice problems. So if you have an appetite, if you have time to do more, you can do the practice problems as well. So on that note, with apologies for the delay in the week 5 programming assignment, I will probably end up closing this session. And yeah, hopefully, Mahesh, that addressed your question from the smiles. I assume that it did, but come over to Discord and let me know if anything was still unclear. Are there any quick questions, especially for people in Zoom? I might, because of the time lag on YouTube, I might miss out on questions that come in there. But if there's anything that was not clear, especially about things that we discussed here, but anything else, then this would be a good time to drop your questions in Zoom. Otherwise, we always have Discord. I hope and assume that everybody is on the Discord room. Yes, Kushagra, sorry, I completely forgot that you had asked a question, but given the timing and also because I think Mr. Atisha is also here and he would have to close this session. So I would hesitate to delay this further, but I think, we can definitely discuss on Discord. We can even do like a informal voice channel if required, but otherwise we can just discuss it there. All right, so on that note, once again, thanks to everybody for joining, as I said, especially on a session that was rescheduled on short notice and is happening on a Sunday. Really appreciate it. And thanks to everybody who engaged and participated in the discussion. That really makes this fun for me and hopefully for everyone. So appreciate that very much as well. So I would say good night for now. Hope you keep enjoying the course and we will catch up next week at the usual time, hopefully Saturday, 7 p.m. And I look forward to it. So yeah, thanks everyone. Kushagra, Debashish, Vijay, good night for now and bye-bye. Thanks, Anwar, too. See you around. Take care. Bye-bye. So, Mr. Atisha, I think we can stop the live stream and we can close the Zoom meeting as well. Yeah.
Okay, ma'am. Thanks, ma'am. Thank you
so much.